Start here. All right. So, as I was just saying, midterms, I will be going through them. I teach from 7 to 5. I don't want to go. I'm going to go home and have dinner with my wife, probably relax. There's a good chance I'm not checking anything for fucking rounding errors till Thursday night or Friday. But all of the midterms, I'm going to go through every single question on every single midterm, and I can see what the correct answer is and what you answered. And if it's rounding, like if you missed that rounding mistake and it's like worth 5 points, it'll take off the full fucking 5 points. And I'll go through and go, oh, you just fucked up the rounding? You fucked up the rounding, I'll give you 4.9 back. You'll lose something for rounding, but like.
Nothing too crazy.
Nothing too crazy. So like, if it was just a rounding mistake on a 5-point problem, you'll get like 4.8, 4.9.
So
right now it says 0. So I mean.
Yeah. So if odds are our score will go up if that's the case.
Yeah.
It should go down.
Every once in a while, if someone clearly guessed, I don't know that there's any problems in this version. It's because when I say clearly guessed, it'll be like, do part A and do part B, and they'll have different answers. It's really the same question written 2 different ways. I've seen it.
Yeah.
They'll ask the same question written 2 different ways, and if you answered fucking different ways on both of them, you are just randomly clicking shit. You don't know what you're doing. But very few of them are like that. All right, today, hopefully we get through quickly. Chapter 8 and 9 can be a lot. So let's take a look at chapter 8.
Are we just doing chapter 8 today?
We're doing 8 and as much of 9 as I think we can get done. Hopefully all of it. So, mean of a sample. Let's say, oh, I know I do. I have 3 stats courses right now. I have 3 stats courses this summer. I don't know that the summer course is a great example because it's kind of rushed, and so some people like just gave up really early. But in a normal semester, I often have 3 stats courses. If I take the mean of each class, the mean score or grade score, grade is a letter thing, score is like your average. The mean score in each class is going to be different. Does that make sense? There's no reason to think the average grade for, like, if I average out everyone's midterm and I have 3 different classes, they're going to be the same. And since this changes for each sample, like each class is a sample, since this changes for each class, and a class is like a sample of students at DOS, since it changes, it means that this says that the mean is a random variable. Let me be more specific. The mean of a sample is a random variable. Remember, we use RV for random variable. I wrote it out once. And since it's a random variable, it has a probability distribution. The geniuses in mathematics have found. We're going to call the mean of the sample, this is mu of x bar. So the mean of the sample means. They have found that the mu of the sample means is the same as the mean of the population. And they have found that the standard deviation of the sample mean,
The mean of sample population is,
the mean, so mu is mean and x bar is sample mean. The mean of sample means. So if I took that, so I have 3 classes. I have the average in each class. Let's say all the teachers generate their averages in each class. So we've got a lot of sample means there. We can take the mean of all those samples and have a new mean. It's like the mean of all means.
That's mean of population.
And it will be the same as the mean of the population.
Okay.
The standard deviation of those sample means is going to be the same as the standard deviation of the population, but it's divided by the square root of the sample size. And I'm going to show you this by a simulation in a second. But we're going to write out the paper version of it first, because I think you see the math and then you'll see it on like the simulation. You go, okay, I see it. I think it clicks a little bit. Standard, is everyone done writing? That's quick. So, I love using the standard IQ test. It is a great thing to use. For a standard IQ test, the mean of the population is 100 and the standard deviation is 15. Let's say I do a bunch of groups of 9 people, and then a bunch of groups of 15 people, or not 15, 25 people. So n is 9 and n is 25 for this. So I've got like 100 groups of 9 people. I get their IQ. I find their mean IQ. The mean IQ for this group and the group down here are both going to be 100 because it's the same as the population. So mu of x bar for each of these is going to be 100, or really close to 100. The standard deviation where I have groups of 9 people will be 15 divided by the square root of 9, which is 15 over 3, which is 5. If I find the mean of groups of 9 people, and then I take the mean of all those groups, we're going to have a narrower standard deviation than the main population. If I do the same down here, that's an x bar there. We have the standard deviation of the population divided by the square root of n. The square root of 25 is 5, and the standard deviation we'll see is 3. It's even a lot lower. So like if I were to draw a picture, like let's say this is my normal population, mean of 100, standard deviation of 15. When I do the group of 9, it's going to be taller, but as it goes outward, it's going to go down quicker. So that would be standard deviation where it's 5. So that was the n equals 9 group. And the other one is going to be even narrower and taller, more spiked. This will be the standard deviation where the group is 3, or standard deviation is 3, where we have groups of 25 people. It's kind of like this standard deviation thing is lower because we've already done the average. We found the average, and now we're taking like the average of the averages. And so like all the averages are already condensed down into a smaller range. And so the standard deviation of those averages is smaller than the big picture. I'm going to show you this in StatCrunch in a second. I've done a simulation with groups of, let's see, groups of 100 people. And I did thousands of them. How many did I do? Did I do thousands? How many rows do I got here? Oh yeah, there it is. Jesus, 20,000 rows here. I did 20,000 groups of 100 people, simulated the IQ. So obviously these aren't actual IQ scores, but using the mean is 100 and the standard deviation is 15, we can generate sample like random scores. Check this out. Wait, Jean-Luc is still writing, and I want to make sure you're done. Another way of saying that why the standard deviation is going down is since we've averaged everything out, all the outliers have already been averaged into a group. So now all the like if we had like fucking Albert Einstein here, sure, he's got a really big individual score, but when we threw him into a group, the average of his group may be higher than everyone else's, but his outlier status has been nerfed. We've just really just taken it away because we've averaged it with a bunch of stupid people. Well, stupid compared to him, right? Even averaging his score with a bunch of average people just like decimates his awesomeness when we use that as an average. So I'm gonna come over here and show you this simulation thing. So I got row 1, and you can see we go down to row 20,000. Each row, these are going left to right, 100 rows. The mean is 100, the standard deviation is 15. We just randomly generated scores in there. I took the sample mean of the first 9 columns for each row. This is like doing a group of 9 people. I'm going, what's their average score? And I got a mean, so this 95.77 is the average of the first 9 columns, or first 9 squares in row 1. This 98.22 is the average of the first 9 columns in row 2. And as we go down, there's 20,000 rows like this. The mean is around 100, but notice there's not a lot of big deviations from 100. Like 108 is kind of like the biggest I see from there right now. We got a lot of ones that are pretty close. 99.667. There's not too many that are far away from 108.
109.
There's a 109. Einstein's like a fucking like 180 or some shit like that. We are not going to have anywhere near that kind of average, which means we've kind of, by doing the average of the groups, we've killed all the outliers. Well, they've been assimilated. There's some Star Trek shit for you. We've assimilated the outliers. They don't have their outlier stats anymore. So now when I look at the mean of this group right here, I'll do the 25 as well. The 25 is the first 25 columns of each row. And you'll see that the one that had the, where was it? We had a 108 up here. Where'd some bitch go? 108, when we did 25, it got nerfed down to 104. You said we saw a 109 down here. Oh shit, 101's pretty low. No, not 101's 101's good. 109, it's also been nerfed down to 104 when we did more people. Watch what had, these are some, I've got 20,000 averages for the first 9 people and the first 25 people. Watch what happens when we do the summary. We look at the mean and standard deviation of those 2 columns right there. The mean is around 100 for both of them. The standard deviation of the 9 is no longer 15, it's at 5. Just like we calculated, it was around 5. The standard deviation of 25 people is down to 3. We've taken 15 and divided by the square root of the sample size. It's kind of like, it's fucking magic, if you ask me, that it works like that. But the idea is all the outliers have been nerfed. I don't know if that's a phrase you guys use nowadays. Y'all know what a Nerf gun is? Yeah, it doesn't fucking hurt. So like all the damage that they do to the score, the big mean is gone because they've been averaged out. That's the idea of what we're doing here. Now, we've already started in this example with something that has a bell curve. The standard, the IQ test is a bell curve. It's a normal distribution. Watch what happens if I do a uniform distribution. This is rolling 6-sided dice. And I did them 100 times. So each entry in the first 100 columns is a 1 through 6 and it's done randomly. I don't know, I want to show this. You want to do a histogram? That'll actually work. Looks like it's kind of average. Well, that's not average out. Why is there more 1s and 6? The fuck? 1.2. This is a terrible way to do it. All right, I don't want to do that one. Let me do the histogram. I took the mean of the rows. Here, I did the same thing. I did 5, 10, 25 people, 50. And watch what the graph looks like for them when we do a histogram on the means. A uniform distribution, every die should be rolled about the same, like same side. A 1 should be rolled as many times as a 5 or a 3. When we look at the means though, when we do the mean of the first 5 columns, it looks kind of like that. Very few have a mean of 1 or 6. The mean of 2, now the 1 and the 6 don't even show up on the histogram. The mean of 25. Now the 2 and the 5 don't even show up, but what shape is that?
Bell shape.
It's bell-shaped. Even something that has a uniform distribution where everything should be, it should be a fucking flat line. Roughly a flat line. When we do the mean of the means of the groups, like the sample means, we get a normal distribution. This is when we go to mean of 50, and it's even like the 2.5 and 4.5 aren't even listed here, but it's even more of a bell shape. This is actually pretty neat stuff. There's a rule, there's a theorem about it. And this is the idea of everything henceforth. It's called the central limit theorem. Regardless of the shape of the underlying distribution, the sampling distribution of the sample mean is approximately normal for large enough n.
normal or normally?
Should be normal. I had to add a little note, that little thing with Einstein, how his score gets averaged out. I never used that in class, and I think it works well as a description. Like all the real outliers, when you take the average of the group, he's no longer remarkable. Or his group is no longer remarkable.
Yes.
He's probably in that 108 group or some 109 group, you know, some shit like that. That's kind of crazy.
The underling distribution. I'm just kind of confused on this.
So like the uniform distribution is a flat line. We could have a Poisson distribution where it's skewed. As soon as we start, if we start doing the mean of these different samples and take the mean of those samples, it gets to this shape right here. And since we're usually looking at a bunch of samples, it allows us to do hypothesis testing on sample groups rather than trying to figure out what's going on with the overall population. The population models, or the doing this stuff with the samples models what happens with the population. And in the next chapter, we're going to show how we can infer stuff. We'll do it today. How we can take these ideas and go, okay, this was the sample shit. How does it upgrade to the population? What can we say about the population and be fairly accurate? When we say large enough n, we saw when we had like 25 and 50, the graph was very bell-shaped. But when I had n, the mean was 5, it wasn't that bell-shaped. Like, let me put that back up. 50 was very bell-shaped. 10, kinda. 5, it's kind of got like 2 lumps. Little bell-shaped. But like the larger n got, the more people I used in the sample, the better, the more that becomes a bell shape. That's the idea of large enough n. And so you kind of want to shoot for n to be around, you kind of want like n to be greater than or equal to 30. N greater than 40 is usually better. But some of the book stuff recently is put in 30. So if they don't like 40, use 30 as your answer. Thank you. That's where we're looking at stuff with a mean. We're not always looking at the mean of a group. Like if my survey is about like whether or not someone has a certain trait or not, or if they like Pepsi or not, we're no longer looking at like a mean value, we're looking at like a proportion. So how does this stuff change for proportions? That's, and 8.1 was on means, 8.2 is on doing this with proportions.
Was the final on Friday or is it?
It's on Monday.
On Monday?
There's no class on Friday, I can't make you come on Friday.
Oh, okay.
I'm not gonna come on Friday. But you can show up and try to do the final, and it won't be here for you to take.
So would that be? Okay. So I had to like think about it for a second.
As in 7 days from today.
No, like, that was gonna, because my school was gonna do like the stupid like freshman orientation thing on the 1st.
Oh, that's Tuesday, you're good.
Yeah. So I was like, is that the same thing?
Oh, high school students.
I don't wanna do it though, it's just a bunch, because like, there's not enough people, so it's like, so many freshmen with like, kind of like smaller amounts of like, people being able to guide them. And, I mean, I don't really care about
You
that.
have to do that?
Is this your first time going to the high school?
Huh?
I think it's leading a group.
Oh, you're leading the group. Ah,
That's just.
that's fucked. You got, how'd you get volunteered for that? Did you volunteer or you get volunteered?
The ASB teacher, not ASB, I was Lincoln teacher, Miss Wall. She was like, you're doing it. I was like, the choice is like, do you want your final to be like crude or not? Like I'm like, good, like she's like, do you want to be on my good side right now or not? And, like she's grading the finals. I was like, alright.
Oh, so you volunteered to do this.
I wasn't even in her link crew class, I was in her sportsman class. She's like,
If you'd been doing all your homework though, you wouldn't need to worry about that. You
I
could
know,
just go
but-
stuff your shit up your ass.
we were learning about, dude, she had us like learning all sorts of crazy stuff, like, it was,
God, I wish I was your age again, just young and stupid. I'm not saying you're stupid, but like,
no,
compared to you right now, when you're 10 years older, you're gonna look back at yourself right now and go, God damn, was I stupid. No matter how much you think you fucking know right now, in 10 years, you're gonna be like, what the fuck was wrong with me? I thought I knew everything, my parents were always wrong. Parents aren't always wrong, they're not always right, that's for sure. But like, you learn a lot of shit. The older you get, the more dumb you realize not only that you are, but how much even dumber you were when you were a teenager.
and like, I'm glad I doesn't like get away with it though, right now, so.
You get away with more shit as a teenager,
Yeah.
that's for sure.
I get to like.
There's higher expectations for a fucking 45-year-old than there is for a 17-year-old. We expect 17-year-olds to do something stupid. Your brains aren't fully formed. Your bodies are. Your brains are still growing until you're like 25 or so. They're still like developing into full adulthood shit. Doesn't stop at 21. It's kind of crazy. All right, 8.2, proportions. So we're going to do the same idea with sample proportions. But finding the, let me change
Wait,
colors.
are we moving on to 8.2?
We're moving on to 8.2. So finding the true proportion of a population is extremely difficult. But samples are easy. Like if you wanted to find out what percentage of Americans voted for Donald Trump last election, what percentage of voting Americans, I should say, voted for Donald Trump last election, I guess you could check the polls. They do. This is a bad example. They already have all that data. You can find this shit out. What percentage of Americans prefer the color blue over red? You really got to ask every single American, do you like blue or red? That's the only way to get the true proportion. But if we ask enough people, we get pretty fucking close. That's the idea. Asking 100 billion people is not cost effective, is not time effective, and actually gets pointless when you can ask a certain number of people. This was like the rolling the pigs thing. I showed you guys how adding one more score stopped changing proportions. It didn't change it, but like a tenth of a decimal on a percent. Eventually, you ask enough people, the percentage stops fucking changing. That's the idea here. And so we will model the proportion, we'll give it a P. It's going to be the number of people, let's say, give the response over the total number. This is very much like relative frequency. X over N.
Wait, so what's that P with the L?
It's P hat,
What does it represent?
the sample proportion. We give it a hat so it stands out. We call this the point estimate. P hat is the point estimate. It's an estimate of the overall proportion. I would say I miss being your age because I could do more shit like play video games and stuff like that. But it turns out when you get old enough, you get a good enough job, you can fucking do that again. That's the only time I don't do shit I want to do the most is like when I'm doing stuff with my wife. Like I want to have family time, but like I don't have kids. The kids will kill your video game time. Don't have kids. If you want to have what you enjoy as a child and as a teenager, if you have kids, that's just gone until you get rid of them. Unless you manage to fucking get lucky and then like the same shit you do. But I don't know of any child in the fucking entire world that enjoys the same hobbies as their parents. In fact, they go out of the way to find fucking different hobbies. Right? You'll do shit with your parents, like they want to do game night, you'll do game night, family game night, you're obligated to do it. You don't do it as an adult, you probably won't do it as an adult until you get older and you're like, I'm gonna fucking do this to my kids because I want to spend time with my kids. All right, so P has the point estimate. Let me give you an example. I asked students, in the first Star Wars, and when I mean first Star Wars, I mean episode 4. The original Star Wars, not the fucking Phantom Menace. What did you think of Luke Skywalker? You guys might be the only class that I will have asked, and the majority of you have seen Star Wars. You all have seen Star Wars, right? Who hasn't seen Star Wars? One fucking anomaly. You're an outlier in here. Get out. No. I've asked this where I've had more hands raised that go, I don't know what fucking Star Wars is. Like when I do that Darth Vader slide in the beginning, Lord Vader, I don't know who he is. How do you not recognize the most famous villain in all of fucking movie history? I don't know. I don't know who he is. So I ask him, what do you think? And I give him some options. I say, do you think he's a hero? Do you think he's a whiner? Do you have no opinion about it? Or do you have some other opinion? And I asked 42 people. And the results were this. 9 people said he was heroic. 33 people said he was a whiner. And I got nothing in the other 2 categories. So P hat for heroic. He's a heroic character. P hat is 9/42. These are up to 42. What is that here? How many people thought Luke Skywalker in the first one was a hero? 0.214, or 21.4%. If I had used a good random sample to get those 42 people, rather than just asking my students, this would be an estimate of the population proportion. Let's change, that's a dead pin. If my sample is random. Well, we're still doing that. We still want this bell curve thing, so we still have a mean and standard deviation. The idea of this whole thing is we can do everything as bell curves. So in bell curve format, what's going on? The mean of the proportion should be equal to the point estimate. Well, yeah, it should be the actual, since we're using the point estimate as the proportion of the population, that's how we're doing it. The standard deviation of P is we have the square root of P times 1 minus P over N. This is calculator work. You find these in the calculator. To make sure N is large enough, we have some requirements. We still need large enough N. For a standard bell curve. Bell-shaped distribution. Well, let me not say standard, just for a bell-shaped distribution. Our requirements are, we want our sample size to be less than 5% of the population. So our sample size shouldn't get too big.
Will always be less than 5% of the population.
Yeah. Like, because there's a second criteria. That's criteria A. Criteria B is N times P times 1 minus P is greater than or equal to 10. So this one sets like a minimum, and this one sets a maximum. We don't want N, we want N to be bigger than a certain amount, but we want N to be smaller than a certain amount. The idea is, if we get N to a large enough number here that it ends up being more than 5% of the population, just ask the entire fucking population. You've already asked a bunch of them already. Finish the job. That's the idea. Generally, you'll do enough to meet the criteria of this, and we're going to do some examples of this shortly. We're going to look at some examples from the homework. Do them straight from the homework. In fact, let's do that now. As soon as everyone's done writing this, I'm going to look at, we're going to do question 1, or not question 1, we're going to do question number 8 and 8.1. I'm going to take a look at that. And we're going to look at questions number 2 and 6 in 8.2. We're going to look at some examples here. And I'll have the homework open and work from there. And as I need to do calculator stuff, I will switch back over to the document camera. We'll do it here so you can see it. But if it's not calculator work and it's just already on the screen in StackCrunch, we're just gonna leave it there. I'm gonna talk about it verbally and not have to write it all down. Everyone ready? Okay. Let's flip that page over. Get my trusty calculator out. And let's come over here and look at homework. Okay, 8.1, number 8, they give us a simple random samples. Oh, I can make this bigger. So it's easier to read. A simple random sample size of n equals 81 is obtained from a population that is skewed right with a mean of 76 and a standard deviation of 9. So the 76 and the 9 are the population. The sample is 81. Remember, if you look at your equations, when we do the standard deviation, when we do the mean of a sample, it should be the same as the mean of the group, of the population. So the mean of this sample should be 76 also. The standard deviation, though, is the population standard deviation, which is 9, divided by the square root of n. So I'll write that shit down because we need this in a second. So I had population had a mean of 76 and a standard deviation of 9. And it even tells us that the population is skewed right. Then they did a sampling distribution with n equals 81. This changes our mean. Well, our mean doesn't change. The mean is the same. The mean of the standard or the sample mean is the same as the mean of the population, which for us is 76. The standard deviation for X bar is the standard deviation of the population divided by the square root of n, which will be 9 divided by the square root of 81, or 9 over 9 is 1. A lot of students, if I don't go over this in class, put in the standard deviation of 9 and forget to change it to 1. And when they ask you a bunch of shit, all your answers are wrong because you've used the wrong standard deviation. By doing this sampling distribution, we have made it approximately normal. By doing this sampling distribution. In fact, that's question A. Question A is, what is the distribution or sampling distribution shape? Approximately normal is your answer. That's actually part A. Part B, I'll write up the things so you can see them now. They say, what is the probability that X bar is greater than 77.7? What is the probability that X bar is less than or equal to 73.8? And what is the probability that 75.5 is less than or equal to X, which is not, I'm sorry, less than X, which is less than 78.1.
Is that 25? P of 25?
75.5. Since we've showed that this is all approximately normal, this means we can use the normal calculator with the mean at 76 and the standard deviation at 1. The ones we just calculated for the sampling distribution. All right, you guys ready to go look at it? So part A, we said it was approximately normal. They also want to know what the mean and standard deviation is. We calculated this, 76 stayed the same, but the standard deviation was 9 divided by the square root of 81, which is 1. Now they want us to do this stuff. This is stat crunch work. I'm going to say give more help, and I'm going to use stat crunch. Stats, calculators, normal. We said the mean was 76. We said the standard deviation was 1. And we want greater than 77.7. So, and I'll write this on the page, but you can see what we're getting here. Is that big long decimal. I'm going to write them all, but I'm sure I don't need them all for the answer. 0.4456546. Let's see how many they wanted me to have. 4 decimal places, it says. So 4 decimal places is to right there. I look to the number to the right and it says round up. So I'm going to do 0.0446. Come put that in my answer. Ooh, too many zeros there. I click check answer and it says good. If you left your standard deviation at 9, some of you will do this. If you left it at 9, check what happens to this probability. It's a lot different. 0.425, 42.5% rather than 4.4%. It's a lot different. You want the standard deviation after you've divided by the square root of n. Then it asks to do the other ones. So we'll have the same thing up. I can do less than 73.8. And it gives me a value. 0.01390345. I assume it's still 4 decimal places, so 0.0139. And finally, for the between, don't forget that you can click up here and click on between. Put the 75.5 over here, and we put the 78.1 there. And it gives me a nice little number. That's gorgeous. 0.67359804. To 4 decimal places, it looks like 0.6736. Ooh, that's got a little bite to it. Do not come up here.
Would I be able to take the final like earlier a day after, or like would I be able to schedule the like earlier or like a day after maybe?
Isn't the day after when you need to go to the fucking orientation?
Yeah, but I might not go to that. So yeah.
You can do before, but not after. Like I have very little time to get in grades after.
Okay.
We'll talk about it later. Check answer here. Good to go. All right. Let's go take a look at come back to the assignment. I'm going to look at 8.2. This is 8.2. What did I say? 2 and 1 and 6, 2 and 6, 2 and 6. So we'll take a look at question 2. So it says, describe the sampling distribution of p hat. Assume the size of the population is 20,000. And they give us some information. So I'll write this on, I'll move this over to that page. So that was 8.1, number 8. Now we're going to take a look at 8.2. We're looking at number 2. And they tell us the size of the population is 20,000. That's my big N. And they tell me N is 500. And they gave me P is 0.101. Now, this is approximately normal if N times P times 1 minus P is greater than or equal to 10, and N is less than 0.05 of big N. So we're going to check both of these. They gave us all these numbers. We're going to use these numbers. So we've got 500 times 0.101 times 1 minus 0.101. Let's just figure out what that is. 1 minus 0.101. This is 0.899. So I'm going to take 0.899, I'm going to multiply it by 0.101, and then I'm going to multiply it by 500. And this equals 45.4 to 1 decimal place, and this is greater than or equal to 10. That's confirmed. Now we check the other one. Is little n 500, is that less than or equal to 0.05 times big N, which is 20,000? So 500, 0.05 of 20,000 is 1,000. 500 is less than 1,000, so it meets that criteria.
So it is approximately normal.
So it is approximately normal, and they're going to ask us why. And we need to say it meets both of these. And they're going to try to trick you up. They're going to change the inequality symbols in here. So we just got to look for the right answer. So if I come over here, I'm looking for the ones, the bottom two for me say approximately normal. One of them, they both say N is less than or equal to 0.005 N. That's good. C says N times P times 1 minus P is less than 10. That's not the right one. We need greater than or equal to 10. So the answer there is going to be D. Your letter may differ, and it may not, they may give you something where it doesn't meet one of the criteria. So don't just automatically assume it does. Okay? Let's come down and take a look at 6. Oh wait, there's more work on that. Look at this shit. Okay, so they want to know what the mean is. So the mean, I'm probably going to need a standard deviation too. So let's go back to the calculator or screen over here. So they ask what mu of p hat is. Remember, it's the same as p, which is going to be point, in this problem is 0.101. And they're gonna probably ask me the standard deviation, which is gonna be p times 1 minus p divided by n, and then take the square root. 0.101. 1 minus p I already did up here. I'm gonna just put it down right here, so I can write down less. And n is 500. So I'm gonna do that part first, and then I'm gonna take the square root. I'm gonna do square root of answer. I don't know how many decimal places they want, so I'm gonna write them all down. All right. Let's come over here and enter that stuff away. 0.101 was my p. And standard deviation says the 3 decimal places. If I do 3 decimal places, I had 0.13.
Yeah.
All right, that was it for that one. Let's go take a look at question 6. Okay, question 6 for me says, a researcher studying public opinion of proposed Social Security changes obtains a simple random sample of 35 adult Americans. So I'm going to just stop right there. I'm going to write down little n is 35. And ask them whether or not they support the proposed changes. To say that the distribution of the sample proportion of adults who responds yes is approximately normal, how many more adult Americans does the researcher need to sample? So, what the question is asking is, how big does n need to be? If A is 15%, we do 15%, or B, 20%. And we already have 35, so it's more than 35. We need to find out whatever n is and subtract 35. So we're going to use n times, come over here to the calculator, or screen. They gave us n equals 35. They gave us these percentages. We need to find n, what n needs to be so that n times p times 1 minus p is greater than or equal to 10. I'm going to assume, since it's adult Americans, that there's no way in hell we're going to get to the 5% mark. That's a lot of fucking people, right? There's no way n's going to get large enough. So let's find what satisfies this. Don't use this n. We're trying to find out what n needs to be. So don't use this n. We don't know what n is. It's going to be our variable.
Wait, so if we don't need to use it, why do they give it to us?
We're going to use it at the end. Just don't use it in the formula at first. You'll see in a second. I don't know what n is, but I know p is 15%, which is 0.15. So 1 minus p is 1 minus 0.15. And I need to be this to be greater than or equal to 10. One minus 0.15 is 0.85. So I have n times 0.15 times 0.185 is greater than or equal to 10. 0.15 times 0.85 is 0.1275. That needs to be greater than or equal to 10. And if you remember algebra, solving for n, you divide by the thing multiplying by it. I'll divide both sides by 1.275. Ten divided by answer. This says that n needs to be greater than or equal to 78.43. I can't ask 78.43 people. And 78 is too low, so round up. N is 79.
Wouldn't it just be 78 because it's like lower?
No, we want greater than 78.
Oh, okay.
Normally, rounding down, you would round down. Okay? That's an important observation. Normally, we would round down. But we need n to be greater than 70. We need this to be true. So I could either use, if I round down, that would be n is 78. But 78
Is less than.
is not actually greater than 78.43. That's not true.
Makes sense.
So the 79 is. I'm glad you asked. Because normally we round up or round down.
So how do we know whether to use n in the beginning for like the equation, or instead of using it later?
They asked, the way they asked it is how many more adults have to be asked, which means they need a total of, you just have to reason this out. They've asked 35. How many more do they need to ask?
How many more?
So, well, if they have 35 and they need 79, I can do 79 minus 35 and get 44. 44 more people. That will get me 79 people. So they get tricky in there. This is very much starts turning into a thinking class after the math gets done all by the computer and you can start using some reasoning skills.
So does that make n 44?
Yeah. So I'm gonna go over that there and n right real quick. It even says round up to the next nearest integer. Now they want us to do the same thing for 20%. This is literally a rinse and repeat of what we just did. We're just changing p. So b will be n times 0.20 times 1 minus 0.20. We want that to be greater than or equal to 10. One minus 0.2 is 0.8, and 0.2 times 0.8 is 0.16. And I don't know 10 divided by 0.16. But I imagine it's like 60 or something like that. 62.5. I divide by 0.16. I get n has got to be greater than 62.5, which means n needs to be 63. And I've already asked 35, which means I need 28 more. So if I put 28 in. Says I'm good. All right, so that's the chapter 8 examples we're gonna do in class.
Can you go back to the,
Let's take like, I don't know, a 7-minute break or so. Pause, shit, we'll do 2 videos. That was chapter 8, we'll do chapter 9 separately.